Okay, let's get started where we left off with the filtering algorithm. Um, I'm sure you've been doing a lot of thinking about other stuff since you last saw this. So let's just remember what the problem is that we're trying to solve first. So this is an algorithm for determining a belief distribution over the hidden state in a hidden Markov model. Here's a picture of a hidden Markov model. It can go from 1 to numbers as high as you like. And the variables that we will typically be conditioning on, the variables we're expecting to observe the values of, are shaded in at the bottom here. You could talk about like other conditional probabilities and what distribution is implied by the hidden Markov model. But the point of building this model is because we're expecting a circumstance where we have a hidden state up here, so we're not going to be conditioning on those values typically, ultimately. And we have evidence variables down here. These are the variables whose values we're going to see, and then we can infer what's going on elsewhere and predict what's going to happen in the future. So this is the sort of question, well, one sort of question, that we might want to ask. Given all the evidence that we've seen, and so this is E1, comma E2, comma so on up to ET plus 1. That's what this notation means. Conditioning on all of those variables, all these shaded variables, what is the probability distribution? Remember, capital letter, so it's a vector or a distribution over the values that it could take, that this latest hidden variable will take what the distribution over what values it'll take. And you can see, I mean, it's easier to see for these past ones, knowing the distribution of one of these hidden variables means that that's kind of all you need to predict going forward. The technical term is it screens off all the other information. So if you know a distribution over x2, you can forget about E1 and E2. They're not going to tell you anything else if you're trying to look forward. So this is kind of trying to take everything we know up to time 4 and represent that as a distribution over the hidden state at time 4, if we're looking at this diagram, really for any t, of course. And the method, which works because of all this math, which I'll go through again, decomposes this value, which we want to have, into values that are given to us by the hidden Markov model, or we will have pre-computed at the step before. So the overall scheme for this is you go from 1 up to the value of t you're actually interested in, computing this value, and then that helps you for the next one. So you can see that if we've done it for t, we can do it for t plus 1. Okay, so this is the recursive filtering algorithm, and I'm going to review each of these steps, why they work. First step. Left-hand side, this is the definition of the conditional probability. Last time I just told you this is an implementation of Bayes' rule, and it is. I'm just going to go a little more into the details in case that still seemed a bit vague. So that's the definition of conditional probability, the probability of all 3 of them divided by the probability of just the 2 being conditioned on. Here's the right-hand side, again, just replacing the definitions of conditional probability. And you can see that those 2 cancel out. So that simplifies to this. And now what's the value of alpha that makes the left-hand side and right-hand side equal? There it is. And importantly, crucially, this is the same for all values of little xt plus 1. So remember that this is a distribution. It's going to be a value, it's going to return a value for every possible value that big xt plus 1 could take. And so you can recognize if they don't sum to 1 and renormalize. So the left-hand side and the right-hand side, until you renormalize, will give you 2 different vectors. Typically, none of the values will line up. But if you scale the one on the right so that they all sum to 1, now all of the values will line up. So this normalizing term. It doesn't depend on which value of xt plus 1 we're looking at. So it's a constant over all of them, which means we can just rescale so they sum to 1 and this will disappear. Okay. Or you could just call this Bayes' rule if you prefer, but this is just getting into the math a little closer. Okay. Next step. Well, these are the same, obviously, so now we just have to ask, why do these two things equal each other? Yeah. Right. So it's a fact about conditional independence that is given by the model that we're considering, the hidden Markov model. So if we're looking, okay, t equals 3 in this example, if we're looking at the probability of this, given that, it doesn't help us, sorry, did I do that right? Yeah, that's right. It doesn't help us to know what did all these values take. If we know this, that's all we need. Yeah, if we know this, all this information is unhelpful because, I mean, you can actually just read out the probability of this given that from the hidden Markov model. Yeah. 1 colon. Yeah. It is, what it means is E1, comma E2, comma E3 up to ET. So we're conditioning on, it looks like we're conditioning on 2 things. In fact, we're conditioning on t plus 1 things. Yeah. Other questions? Okay. This is like, well, there's another step that looks just like it, but these kind of facts are the key to making inference tractable in an HMM. Okay. So variables are independent of non-descendants given parents. That's the more general way you can read out certain forms of conditional independence from this graph. And if they're conditionally independent, then that means that adding the extra information doesn't change the distribution. Okay, if I know x4, nothing else will help better predict E4. Okay, next one, these two. Okay, this is the same, so why does this equal that? This is, let's see, it's a little easier to go right to left here. So this is the value, no, sorry, it's a little, yeah. I wrote it this way because it's easier to go left to right. Okay, if we have this expression, which is the bottom one here, then here we fold these conditional probabilities together into a joint probability. They're still conditioned on the evidence, but we're doing the probability of little xt first, and then the distribution over xt plus 1 given that. Fold them together into a joint distribution over both of these, given the variables that they're both conditioned on. So that's just the relationship between conditional probability and joint probability. And then going from here to there, we're just marginalizing over all of the values that xt could take. So if you're thinking about the probability that it's rainy, that's going to be the probability that it's rainy and hot, plus the probability that it's rainy and cold. So we're just summing out this other variable, and now we get this. And so this step is kind of going backwards from here to there. And now this is the only thing that changes. Again, we're noting that conditioning on the evidence is extra information we didn't need if we were already conditioning on the value of little xt. Variables are independent of non-descendants given parents. Xt is a parent of, well, xt is the only parent of xt plus 1. And so other information, we may as well discard it. And so now we get back to this. And that's it. That's why this update rule works. Okay. So this is called the forward algorithm. In blue are the things we're calculating successively. So here it is for t, there it is for t plus 1. In pink are the values we're getting from the hidden Markov model. Okay, well this doesn't come from the hidden Markov model, but you just normalize at the end. So let's just think for a minute about what kind of objects these are. This is a vector given by the hidden Markov model because we get one value for every value that big xt plus 1 could take. This is computed in the last step, and it's a scalar, but we have one scalar for each term in this sum. So this is a sum over all the values that xt could take. So we have, let's say all these x's can take n different values. Then we have n different scalars, one for each term in the sum. And here we have n different vectors, one for each term in the sum. So this will, in total, be like n squared numbers. This will be n numbers, and this will be n numbers, where n is the number of values that the hidden state can take. So the forward algorithm looks like this. We take in our distribution over the hidden state at time t. We add in the evidence from time t plus 1, and now we get a quick way of coming up with of our belief distribution over the hidden state at time t plus 1. So we can split these up into a prediction component, an update component, and a normalizing component. And this might look a little confusing for t equals 0, which is how you get off the ground, but just note that this is empty. E1 to 0 is actually conditioning on nothing. That's more for when you're going back and looking at this later if you need to. Okay, so the cost per time step is order cardinality of x squared. So that's just the size of the set x, the number of states that we can be in. So excellently, the time and space costs are constant, independent of t. It would not be very good if it took you longer and longer to think about what's going on in the world the longer you lived. You want some way of processing the relevant facts about the world that you'll need for acting intelligently in a way that is constant in time and not getting slower and slower as you age. Or if it does get slower and slower as you age, it shouldn't be getting slower very fast. Okay, so that's great. Unfortunately, this quadratic term in the size of the state space is infeasible for models with many state variables. Bad news. But the good news is that means we get to invent really cool approximate filtering algorithms. And I'll talk to you about some of those either later today or next time. Okay, same thing in linear algebra, the same algorithm. If we have a transition matrix T and an observation matrix O sub T, then the observation matrix has state likelihoods for ET along the diagonal. So let's say, so this would be like, well, we can look at it here. So the example I showed you last time was about the hidden state being sunny and rainy, and the evidence being whether your supervisor brought their umbrella down to the nuclear bunker that you're stationed in. So here's our transition matrix. So if we have sun at time t minus 1, here's the probability distribution over sun and rain at time t. If we had rain at time t minus 1, here's the probability distribution over the weather at time t. So this is our matrix T. And now, given the weather, sunny or rainy, here is the distribution over whether you see the umbrella. If it's sunny, 20% chance you see it. If it's rainy, 90% chance you see it. So if we observe that the umbrella was seen, then we convert this column into this observation matrix. It's a little hard to think about what this matrix means. So it's the relative probabilities assigned by the various states to the outcome you've actually observed. So if you see, depending on what you see, depending on what evidence you get at time t, you'll use a different observation matrix. So that's why this is subscripted t. It's not the same at every time step. It depends on what evidence you actually saw. You look at the evidence you actually saw, you go to that column in the conditional probability table for evidence given the hidden state, and you turn that column into the diagonal of this matrix. If you prefer to think about it not in terms of linear algebra, this is redundant with the slide that I showed you before, and you could just think about it like that. If you're excited about vectorized code and Python, this would be how you do it. And so then the filtering algorithm looks shorter. That's what it is. You do a couple of matrix multiplications from the vector you started with, and you end up with a new vector. So if you know anything about GPUs, maybe you can see that this would run pretty fast. Okay. So back to our weather example in more detail, and this is important, the starting probability distribution at time 0. So we have the weather at time 0, and we don't get to see it directly, but we start out with a belief distribution, a probability distribution or a vector over the values that it could take. And now we see that there is, I think that's what the green means, that there is an umbrella at time 1. So now what do? We predict, following this, so this is not based on the evidence yet at all. We predict if this was our distribution over the state at time 0, this is the probability distribution over the state at time at time 1, just using the transition matrix. But now we update that given the fact that we have seen the umbrella at time 1. So this is the update step. So remember, I decomposed the step into predict, update, normalize. Here's predict, there's update, and, that's update and normalize, I guess. That's done in one step. So first you'd update, you'd multiply both of these times some numbers, and then you renormalize. Now we go on to the next one. We predict just based on the transition matrix, and then we update. And we can keep doing these steps alternately with normalization folded into this update thing, and we can keep coming up with a running estimate of the hidden state, that is the weather. Okay, here is, no. Is this a video? No, the video's coming later. Okay. So the example that I'm going to show you guys now is a video of Pac-Man hunting invisible ghosts with sonar. So to Pac-Man, the state is hidden. The state includes the information about where the ghosts actually are. And note, this is a valid concept of state, because if you know that, you can know how it's going to go. You can know the probability distribution about how it evolves. You don't need to know what came before. But Pac-Man's not observing this state fully. He's only getting evidence about the state. Certain states are more likely to give him certain values of this evidence variable, and so he can see those values and then infer back to which likely states caused it. And this is he can see like the distance approximately and the direction approximately to all four of these ghosts. But his sonar is noisy. So here's a video of it. Okay. Okay. So I'm just going to pause it for a second. Can you guys see that okay? Or is it too bright up here? Okay. The distributions are representing the probability that he assigns to that particular ghost being in that spot. And he's kind of figured out, oh, he's got the blue one. He's kind of narrowing down where the red one is. He's trapped it, there it is. Now he's going for the orange one, there, he's got it. So he's acting rationally with respect to his uncertainty. There he goes, he's got them all. So, as he gets more and more pieces of evidence, he filters that in, basically, to update his belief distribution about where the ghosts are. And even though he doesn't know where the ghosts are, he knows how their states, the distribution under which their states would change, depending on where they are. So he can update, so that's his transition model. And so then both of those pieces are how he updates the belief distribution over time pretty quickly. Okay, so now we're going to turn to a different question, not keeping a running belief distribution over the current state, but coming up with the most likely explanation for all of the past pieces of evidence. Different problem, different algorithm. The algorithm is going to end up looking very similar. Okay. So I just told you about the filtering problem, and now we're going to go to the most likely explanation problem. So that is coming up with assignments of values to all of the previous hidden states to maximize the likelihood of the evidence that was actually seen. And some applications of this include speech recognition and decoding with a noisy channel. I think I mentioned those to you last time. Okay. So this most likely explanation problem is actually going to look quite similar to a shortest path problem. In this case, it's the most probable path. So here is a state trellis. That's what this way of drawing things is called. It's a graph of states and transitions over time. So here are the possible states, sun and rain. Obviously, there could be many more. And these arrows represent the initial probabilities of those states, and these arrows represent the transition probabilities. So all of the outgoing arrows from a given state will sum to 1. So these will sum to 1, and these will sum to 1. And we're interested in the argmax over all the values that all the variables could take of the probability of those variables given the evidence we've actually seen. Okay, this is going to be proportional to the joint distribution. And this is going to be a positive number, and so if we're taking the argmax of this expression, that's just going to be equal to the argmax of this unnormalized expression. And we can decompose this into conditional probabilities. So this is equal to the probability distribution over x0 times the probability distribution of x1 given x0 times e1 given x1 onto the next times the probability of x2 given x1 times the probability of e2 given e1, and so on for x3 and x4 and on up to little t equals big T. This is basically, the fact that this equals that is basically is the point of the hidden Markov model. The hidden Markov model is saying you can decompose this in this way. And we can go, if we want to make this look like a shortest path problem, the way we do it is we take the logarithm of this. Well, the maximizing a function is the same as maximizing the logarithm of the function, because the function always increases when the logarithm increases and vice versa. And so then if you distribute this logarithm through, the products become sums. If we take the negative, now it's an argmin. And since it's an argmin, this looks like a shortest path problem, where each of these are minus log probabilities. Minus log probabilities are always positive because probabilities are less than 1, so the logarithm is less than 0, so minus the log is positive. And in this form, it's basically the same as a shortest path problem. We'd be trying to find the shortest path through to the end. So that's just another form, if you prefer. Okay, so each arc here, and I started with this actually, each arc here represents the transition probability from xt minus 1 to xt, and the weight of that, sorry, it's not just the transition probability, it's also times the probability of the evidence given the resulting state. That needs to be folded in here at some point. So arcs to initial states have just probability of that initial state. And the product of weights on a path is proportional to that state sequence's probability, or you could say the sum of the negative logs of the probability is within a constant of the log probability of the whole. So the forward algorithm computes sums of these paths. Forget what I said about the logarithms. This is the sum of the paths that are products of probabilities. And the Viterbi algorithm, which I'm going to talk to you about now, just finds the best path. So the forward algorithm is kind of looking at all the possible ways you could have got to a certain state to give you its ultimate probability. But for this algorithm, we're just interested in the best path. So whereas the forward algorithm it has a sum here, the Viterbi algorithm has a max there. And that's the only difference. Yeah? Because if we're, so really what we care about is ultimately what we care about is the argmax. So we care about which path got us there, not the number that it comes with. So it's not so much setting alpha equals to 1, it's just ignoring it. Because if you have a bunch of options and you're trying to take the argmax, pick the one that is the highest. If they've accidentally gotten multiplied by 0.2 first, that won't change your answer. So yeah, these technically are not probabilities of paths. They are scaled probabilities of paths, but we don't care about the scaling factor if we're ultimately just going to take the maximum. Good question. Here, we do care about the absolute probabilities, so we have to scale them. There is the attendance code for today. Any other questions about the Viterbi algorithm, how it compares to the forward algorithm? Yeah.
So for the forward algorithm, if we only want to find it for a certain time step,
Mm-hmm.
we have to normalize at each time step between that to find it, or could we just normalize at the end?
You could just normalize at the end. Yeah. Yeah, the way I showed it to you, we were normalizing every time. But yeah, you don't need to. Okay. Here's an example. We have our favorite simple weather HMM. And now let's say that these are the evidence variables we've observed. There was an umbrella here, no umbrella there, yes umbrella there. Here are our probability. Well, they're products of probabilities. So, moving forward, these get values of 0.5. And now we look at the paths to both of these that maximize the product. So do we want 0.5 times 0.18, or do we want 0.5 times 0.06? Obviously, we want that. And coming from here, do we want, sorry, it's hard to see, do we want 0.5 times 0.09 or 0.5 times 0.63? We want that one. So that's our, that's the one that maximizes the product of the arcs along the way. And now here are our new numbers. They're not normalized. And now we go here and we want to see which path is the most likely way through there. And 0.09 times 0.72 is smaller than 0.135 times 0.24. So we use that arc. Same sort of question. And for this one, we use this arc. Update our values by the product of this and that, or this and that. Continue on to the next. There we go. And you'll notice these numbers are getting small because we're not normalizing. But it's okay because all we care about at the end is taking the maximum. And finally, this number is bigger than that number. That would be the taking the maximum step. And so the path that we end up with is the one that got us there. So that's the most likely path. So think about what this means for a second. The most likely explanation for umbrella, no umbrella, umbrella was that it was raining all 3 days, but he forgot his umbrella in the middle, rather than rainy, sunny, rainy, or rainy, sunny, sunny, because we know something about the fact that weather tends to persist. So it's using that knowledge to come up with a better estimate of what's going on. Okay, the time complexity of this, getting up to big T, is quadratic in the size of the state space, linear in the total duration. The space complexity is just linear in the state space. That's nice. And the number of paths, technically, that we're optimizing over is the size of the state space to the power of T. So that's great. I mean, obviously we couldn't do this one by one. We couldn't consider every single path. And so you can think of this as a very impressive way of finding the best out of exponentially many without having to even look at all of them. I mean, it's pretty basic, but still, it's, you know, you're doing, if you were very naive, it would be a very slow answer to compute. And this is a more intelligent way of doing it that is vastly faster. Yeah.
Where's the fact that what are the temperatures factor into this?
So this is encoded in this transition matrix here. So you can see that the probability of sun is 90% if it was sunny the day before. How do these tables affect these numbers? This arc is going to be the product of two probabilities. It's going to be the probability of rainy given sunny the day before, so that's here, times the probability of no umbrella given rainy, so that's here. So you can see that small numbers here make these numbers in the arcs small also, and big numbers make them bigger. So that's how this information from the hidden Markov model is affecting these numbers on the paths. And here's what I was talking about before. If you take the negative logarithm of all these numbers, now they're all positive numbers, and it's the same as just trying to find the shortest path. So I don't know. apparently this guy, Viterbi, patented this algorithm and made a huge amount of money from it because it's used in signal processing and coming up with the most likely signal given the noisy stuff you observe. And it seems to me that if you've just taken the negative, if you've just done e to the negative of a shortest path problem, maybe you shouldn't be allowed to patent it, but I don't know. So yeah, it's isomorphic to a very simple algorithm, the coming up with the shortest path through to the end. Okay, technically the shortest path problem, you have one terminal state, but if you want to really reduce it to the shortest path problem, you could just add arcs of 0 to a single end state there. And, you know, we've done search through graphs with costs. Viterbi is essentially a breadth-first graph search. You could think about what it might look like to use heuristics to try to do it faster, like with A star. But we're not going to go into that. Okay. The next topic is dynamic Bayes nets and particle filters, which are how we can do inference in dynamic Bayes nets. Here's a little drawing of a dynamic Bayes net. So, we just talked about hidden Markov models before we talked about Bayes nets, and this is going to basically combine them together in what hopefully will strike you, if not immediately, at least in retrospect, as the obvious thing to do. So, the issue with hidden Markov models and the algorithms that we have to solve them is that the time they take is quadratic in the size of the state space. And the solution to that before we thought about time was a Bayes net. So a Bayes net has many different variables. If you looked at the joint distribution by taking the cross product of all the different values that all the different variables could take, it would be exponentially large. You would need an enormous amount of data to fill in every cell of the table, of the joint distribution table, that says, okay, what's the probability that this variable takes that value, this variable takes that value, this variable takes that value, and so on. There's just so many questions you have to ask that and so the point of a Bayes net is to represent that distribution with many fewer numbers, make it much easier to learn, given knowledge about conditional independences in the variables of interest. So we can apply that same sort of idea when we have time. And then it becomes like a hidden Markov model, but now we call it a dynamic Bayes net. So we want to track multiple variables over time using multiple sources of evidence. So the idea is to repeat a fixed Bayes net structure at each time, and the variables at time t can have parents either in time t or at time t minus 1. So maybe this picture makes a little more sense. Here's the slice of the dynamic Bayes net at time 3, I guess, and it can have parents in the same slice, or, and this isn't really pictured, it could have parents in the slice before. So here are some hidden variables, and here are some evidence variables. This is at time 1. Same hidden variables, same evidence variables at time 2. Their parents are either in the same time slice or in the one before. There's time t equals 1, there's time t equals 2, and so on. And the conditional probability table for this is identical to the conditional probability table for this. It's just referring to different parents. But it's referring to analogous parents. Okay. So every hidden Markov model is straightforwardly a single variable dynamic Bayes net. So we just have one variable, one hidden variable, one evidence variable. Any hidden Markov model is clearly just a simple example of a dynamic Bayes net. It also goes the other way, where every discrete dynamic Bayes net is a hidden Markov model. The state is the Cartesian product of all of the dynamic Bayes-net state variables, looking like this. So if this is our dynamic Bayes-net, we have 3 different hidden variables, x, y, and z. And here's the, let's say each of them can take 2 values. Here's the conditional probability table for this given that, the transition matrix. And you can convert this into this 8 by 8 transition matrix because there's 2 values this can take, 2 values this can take, 2 values this can take, so 8 values that this joint variable can take, so 64 numbers you need to write in. You can see why you don't always want to do this if you have lots of variables. So if you have sparse dependencies, you can get exponentially fewer parameters in the dynamic Bayes-net version compared to the hidden Markov model version. So if we have 20 Boolean state variables with 3 parents each, for example, then the dynamic Bayes-net has 20 times 2 to the 3rd parameters, that's 160, whereas the hidden Markov model has 2 to the 20 times 2 to the 20, that would be how many rows and how many columns, which is about 1 trillion parameters, which might still be doable, but if you get more state variables, then it'll quickly become, like even if you get 5 more state variables, it'll quickly become not doable. Okay. First, let's talk about trying to do exact inference in dynamic Bayes-nets. Well, it's really a Bayes-net. It's just a Bayes-net where a lot of the conditional probability tables happen to be the same. So we can try to use the same techniques from inference in Bayes-nets in dynamic Bayes-nets. So we can do variable elimination. We can unroll the network for t time steps, basically turn that into one, just call that one Bayes-net, and then do variable elimination to find the same sort of thing we were interested in the HMM setting, the probability distribution over the variables from the last state given all of the evidence. So we might be interested in, well, this is saying just a particular variable, but we could look at any subset of variables of interest in the last state. That would be an offline method. An online method would be to eliminate all variables from the previous time step and store factors for the current time only. And the problem that arises here, the largest factor contains all variables for the current time plus a few more. So it pretty quickly becomes infeasible. The cost is exponential in the time t. Okay, before getting to an algorithm for approximately, so that would be exact inference. Before getting into an algorithm for doing approximate inference, I'll walk you through an example for the use of dynamic Bayes-nets. This is from Stuart Russell's group many years ago. He was the one who created these slides. So I might not be able to speak to it quite as well as he can, but I can give you the idea of what's going on here. So this is an ICU. That is a premature baby. Modern medicine is a miracle. Babies that would be like basically certainly dead, given how premature they are, now can survive like 95% of the time. It's just, it's fantastic. And all these tubes are coming out of the baby and going in, monitoring what's going on, administering drugs when needed. And so this is the setup that keeps them alive. And I don't know. Since I've had a child, that picture is just so much more moving to me. So here's what all the values can take in this in this setting, or here's what all of these things are in this setting. So the state are the variables describing this physiological state of the patient. The evidence are the values obtained from the monitoring devices. The transition model it comes from stuff we know about physiology, how things are likely to change over time, and how the sensors are likely to change over time. And then what we're interested in are pathophysiological conditions, that is, bad things going on with the patient. So we want to use the evidence and a transition model to infer things about the state, and then infer things about problems. So here is a toy dynamic Bayes-net for heart rate monitoring. So there's the resting heart rate. That's a stable property of the patient. And then that affects the true heart rate. The true heart rate also depends probabilistically in some way on what it just was a second before. There's also patient movement, which will affect patient movement later. This could lead to the ECG being detached or the pleth being detached. I don't know what a pleth is, but apparently it can be detached. And different measures of the heart rate will come from the heart rate is measured in different ways. And so here's a diagram that aims to capture the causal structure and therefore aims to capture a concise way of representing the joint distribution over all of these variables. This is the fraction of oxygen that's in your blood. So I guess it's also monitoring that. Okay, so that's the state variable that we're interested in this toy setting. These are sensor variables. That's a sensor state variable. It's another state variable, really. It was just some flavor text saying it's a sensor state variable. And this is a parameter variable for the whole network. And here's an example of using this to infer the hidden variables over time. So we have this pink line. The pink line and the blue line are two measurements of the heart rate. And the dashed green is the inferred resting heart rate, and the red is the inferred current heart rate. And what this system is inferring is that when these jump up like this, that's not indicative of the real heart rate. It's more likely that that was due to patient movement. Sorry, I'm skipping it. There's a future example where that's what's going on. What it's recognizing in this setting is that the real heart rate is going up, maybe not quite that much, but the resting heart rate is probably around here. So it can detect that this is the heart rate under movement rather than this being the resting heart rate. If you just tried to average all this for the resting heart rate, you'd get a worse estimate of the resting heart rate. It can tell that this region and this region are probably more indicative of the resting heart rate using the dynamic Bayes-net. Here's the guy, apparently. Okay, here's an example where some of the peaks are actually not really reflecting what's going on. So, on the top here, we have measurements of heart rate and blood pressure. Here we have measurements of the concentration of oxygen in the blood, different places in the blood, also intracranial pressure. And here we have measurements from the ventilator, like lung stiffness, CO2 concentration, a few other things. And all of these spikes here, these spikes there, those spikes there, are in fact not real. They're not measuring what's actually going on with the patient. They're artifacts with other causes. These are probably coughs down here. If you have a ventilator, which like puts a giant tube down your throat, it is extremely uncomfortable, and you will often try to cough it up, I think even if you're not conscious. And so these are not real lung stiffness spikes. If your lungs became that stiff all of a sudden, it probably wouldn't go right back down to being perfectly normal immediately after. And so if you're using a dynamic Bayes net to figure out what's likely going on with the hidden states given these measurements, you can tell that probably everything is normal there. So we've gone past the toy dynamic Bayes net before. Now we're thinking about one that is keeping track of many, many more things. Other things to keep track of are all the medicines that are administered to the patients. Apparently they showed this to some doctors, and the doctors were immediately horrified because they realized that pain medication was administered a lot less after medication that immobilized patients, because they were only giving the patients medication when they were like visibly distressed. And so it seemed like they were just kind of putting them in a more or less a straitjacket made out of drugs and then not giving them pain medication. And so I think this encouraged them to keep giving them pain medication. But that's a bit of a digression. So these are all the different drugs that might be administered at different points in time if you're in the intensive care unit. So that also can provide information about what the things you're seeing mean. Here's just a really low-level example for blood pressure measurement of why it can be so helpful to have some understanding of what's causing the measurement to get a better understanding of what's going on. So if you go to get your blood pressure checked, they'll like put a cuff on your arm. It'll stop circulation for a while, make some measurements, deflate. A, that's slow, and B, you can't constantly be cutting off circulation to the patient just to get blood pressure measurements that are very far apart. So what they do is they have a catheter, also used for putting solution into you or taking blood draws. So the catheter goes into your wrist. Here's the stopcock that allows you to get blood out that way. Here's the tube where the fluid comes in from some bag. It's up in the air, so there's some pressure from it. And here is an input that the pressure is basically measured there. And normally, this is measuring your blood pressure. But if this stopcock gets opened, then there's, and it's opened all the time, if blood is drawn to check for something else, then there's a little blip where it's not actually measuring blood pressure. If something goes on with the bag, then it's actually measuring the pressure of the liquid in the bag. So here are some pictures of bag artifacts at a 1-second resolution. There's something called zeroing. I forget what that's about, but that can also lead to artifacts in the measurement. So this is a 1-second resolution. This is a 1-minute resolution. Kind of much harder to see that something shady is happening here. And here is a more elaborate dynamic Bayes net for inferring the actual blood pressure given the observed diastolic, mean, and systolic blood pressure. So I can't remember which is systolic and diastolic. Anybody know? Which is the higher one? No, nobody's studying that kind of stuff here. Okay. One of these is systolic, one of these is diastolic. That's got to be the mean, although who knows really. So these are the measured, in pink, these are the measured blood pressures. And at 17 minutes, they all reach this same insane value that would mean that you're like in a very bad spot. But the dynamic Bayes net infers, so it starts out unsure of what the bag pressure is, but it infers at this point that's probably the bag pressure, and the actual blood pressures are probably actually probably somewhere in here. We're probably not looking at the actual blood pressures, with our observed blood pressures. And so it can tell that this is really probably what's going on. Here is the probability that it assigns to the valve being open to the bag, which causes it to be measuring the bag pressure. So for the detection of bag events, I'm not going to go into exactly what an ROC curve is, but maybe some of you have seen it in other contexts. Basically, it's good for the curve to be hugging the top left here, and this is what the dynamic Bayes net allows you to do. This is what the dynamic Bayes net allows you to do, so that's pretty good. Other methods are way worse. Okay, why is it so important to not, okay, so what's the big problem? Like, the sensor says the blood pressure is like really high, but you can always just have someone come and check if it really is. So maybe this isn't such a bad way to have an error. Well, alarms are always going off in ICUs, so much that what happens when an alarm goes off in the ICU and starts beeping is someone comes over, if they have the time, and they turn off the beeping. Because it's just, these are all the alarm events. They're coming out both ends. There's just not the bandwidth to take all of them seriously. Here's what you get if you're kind of accounting for the fact, if you can recognize some of these errors you can recognize some of these measurements as essentially erroneous. And these apparently were real moments where, you actually did want to come in and check on the patient. So this is great. Yeah, much better. Okay, so that's an example of using dynamic Bayes nets to save people's lives, or at least save ICU nurses' attention, which indirectly saves people's lives. Now let's talk about algorithms for doing inference in dynamic Bayes nets. The algorithm we're going to talk about is called particle filtering, and it is pretty simple. At least there's not as much manipulating symbols as in the forward algorithm. Okay, we need a new algorithm. If the size of the state space is more than 1 million or so, exact inference becomes infeasible. Likelihood weighting fails completely because the number of samples needed will grow exponentially with t. I don't know if you recall from Cam's lecture a couple times ago, if the evidence is coming at the end in likelihood weighting, it's not really guiding your samples very much. So you'll be going through your Bayes net, or dynamic Bayes net in this case, sampling values for all the different variables, and then you get to the end and you realize it's totally inconsistent with some evidence that came at time t. And so now you have to downweight this into oblivion. The sample hardly counts for anything. And the one that does the best will probably do a lot better than the rest just because it gets lucky. So you'll have a few samples that get lucky and don't get downweighted to oblivion because they happen to predict the evidence. But you'll need to be running so many of these, exponentially many of these, to get samples of the hidden variables that aren't vanishingly unlikely according to the evidence. And as time goes on, it just gets worse and worse because there's so many opportunities for the likelihood to go down. So here, and this line at the bottom is going to be the method that I'm going to tell you about. These lines up here are what happens for likelihood weighting depending on how many samples you're using. Basically, the more samples you're using, and this is, well, like this compared to that and this compared to that is dectupling the number of samples. And it just kind of delays the inevitable, where after a certain amount of time, the error, this is the average absolute error, is just going to go up to really high values. So likelihood weighting doesn't work, essentially. So we need a new idea. When we're doing, this is a picture of likelihood weighting again, kind of showing you visually what happens. So these are the actual states, and we're getting evidence that kind of tells us it's around here. If we do likelihood weighting, where we're not changing the samples at all, we're just running them forward. So at time t equals 2, here's our distribution over the state. At time t equals 7, here's our distribution over the state. We're just running them through, and at the very end, we're down-weighting the ones that are bad. So all these get down-weighted basically to 0, and really this one is going to get down-weighted the least, and it's going to be basically the only one we take seriously. I mean, maybe we'll take these and that a tiny bit seriously, but not really. I guess actually we care about proximity to here, so maybe these two we'll take seriously, and the others not really. And if you look at this, you can see how much wasted effort there is. Because like all these things, I mean, already you can see, okay, these ones, they're not going to really be helpful. I mean, you could predict that these are not going to be the ones that are taken seriously at the end. By taken seriously, I mean have a non-negligible likelihood at the end. So the problem is that sample state trajectories go off into low probability regions, ignoring the evidence. And we have too few reasonable samples by the end. So the solution here is to kill the bad ones and make more of the good ones. In this way, the population of samples stays in the high probability region. This is called resampling or survival of the fittest. It's been proposed independently by a few different people because, well, it's pretty straightforward. So this is called particle filtering. These are our particles, and we're going to filter some of them out. So we represent the belief state by a set of samples. So this might be the true underlying belief state that we would have if we did reasoning, if we did the inference exactly, but we represent it like this. Ultimately, we're going to get an algorithm where the time it takes per step is linear in the number of samples, in the number of particles, but we may need a large number of particles to do well. So this is how we represent the distribution, and we would turn it into, well, yeah, if we wanted numbers out, we'd do it like this. We'd say that we'd basically count the number of the fraction of particles that are there. So that's why this is 0.5, 0.2, 0.2, and 0.1. So a particle is a possible world state. That is a possible assignment of values for each variable at a single time step. And this is, for example, how robot localization works in practice. So a representation of a probability distribution over X, and this is really all of the state variables, is now a list of relatively few particles, at least compared to the size of a potentially exponential state space. Because if we have, 10 hidden variables, each with 2 values, this would be 2 to the 10. So here are our particles. They're apportioning our probability mass to each of these different possible hidden states. And these colors don't mean anything. It's just so you can track the particles as the algorithm progresses. So here's our belief distribution over the hidden state at a given time. Sorry, I thought something else was about to come. Okay, so the probability distribution over the hidden state is approximated by the number of particles with that value. So that means we're going to assign 0 probability to a lot of possibilities. So we're assigning 0 here. It's not really going to be 0, but it's probably going to be small. The more particles we have means more accuracy. It's like a frequency histogram. And often what we'll want out of this is a low dimensional marginal. So we won't our questions will not typically be of the form, are ghosts 1, 2, 3 in 2, 6, 5, 6, and 8, 11? We'll often be interested in pieces of information like where is ghost 1? And the estimates of low dimensional marginals will tend to be more accurate. Here's a little caveat for you that I'm not going to get into. Really, everything's going to be accurate, but for very small probabilities, like if you're interested in a probability of 1 in 1,000 and the error is 1 in 1,000, you might be more annoyed about that error than if the true probability is 50%. Okay, here is why they are called in. Here is how we go from a belief distribution at state t to state, from time t to time t plus 1. So we have particle j in some state, xt, and then we sample a new state directly from the transition model. So we just sample from the distribution over where that particle is likely to go, or what the next state is likely to be, the distribution, given what this state is. So here is a particular value that big xt could take, little xt. Here is a distribution over what xt plus 1 could be, sorry. And now we sample from that distribution. So this green particle becomes a distribution, and then we sample from it, and now it's a new green particle, basically. And the transition model for this is like kind of moving clockwise, but a little noisily. So this green particle's gone there, this blue particle's actually gone backwards. Then what we do is we do an update step. This evidence that we get at t plus 1 is going to be factored in. So as in likelihood weighting, we weight each sample based on the evidence. So each sample will give us some proposal of what the hidden state is, and then we say, okay, well, there's your proposal, but how likely is the evidence that we've actually seen, given that proposal? Not so likely? Bad. You get a low weight. Pretty likely? Okay, we'll only downweight you a little, which is a lot better than what the other guys are getting. So this this green particle is apparently pretty consistent with the evidence. This blue particle is not so consistent with the evidence. And so they're downweighted. And so I'm showing that to you as if their sizes are getting smaller. Then we renormalize across all the particles, so scale them back up. And now these are they're still relatively much bigger than these ones, and they all sum to 1. And now we have a new distribution, and we resample. So rather than just going forward with everything, some of them downweighted, we resample, we choose from this weighted distribution, we draw with replacement. And so now, in this example, this blue particle was never sampled in the next step, but the green one was sampled twice. So now there are two separate particles that are derived from the green particle. They can evolve differently because when we go on to the next step, the way that particle moves forward, it's sampled from the transition probabilities. And so this moves forward, and it's focusing our samples on the higher probability parts of the space. So there's our prediction step, moving it forward. There's our updating and reweighting step. And there's our resample step. And then we repeat. So it's just those 3 steps in succession. Sampling from the transition matrix, reweighting the particles, resampling particles according to their weight, and then repeating. This is a consistent algorithm for sampling. You can see a proof of that in the textbook, provided that the probabilities assigned by the dynamic Bayes net are not too small. If you had probabilities that were 0, you there are a couple ways things could go wrong. Okay. And then you get something that's down at the bottom. It can go on and on and on, and the absolute error will stay very small. And this is just with 25 particles. Okay, here's an example of this particle filtering method. Simultaneous localization and mapping. The robot doesn't know the map or the location, and the state consists of two things, well, three things: the position of the robot, the orientation of the robot, and the map. All of these are unknown. And this caveat, I'm going to skip over it for now, but it is important because, well, think about how the state evolves. The map is never actually changing. If you have a map, if whatever the map is at time t, it's the same map at time t plus 1. So all these, there are going to be a lot of zeros in the transition probability matrix, which messes with the particle filtering algorithm. Basically, whatever particles you sample at the beginning, whatever maps are associated with them, those are the maps you're stuck with. There's no step in the particle filtering algorithm where you could generate new maps if maps aren't transitioning from one into a different one. So really what I'm about to show you is not purely particle filtering. There's some other tricks going on. But at least for the position and orientation, particle filtering really is what's going on here. The transition probabilities will say, you know, given that this was your position and orientation, given that we took a certain action, what's the probability distribution over transitioning to a different state in the future, a different position and orientation. And here is a video of this. And this is the last thing I have for today. So you can see, what you're about to see is when it closes the loop, it's all of a sudden kind of combining information that it saw before on the last loop with information from this time, and that's narrowing down its beliefs about where it was the whole way around. Because, you know, maybe it wasn't sure, was I going like this way or that way? Hard to tell. But once I map up how I got back to where I was, then I can be sure, you know, it's easier to be sure where I am, where the walls are. So it's building out a map now. It's at no point in time is it completely sure exactly where it is, but as it's resolving that uncertainty based on seeing similar things twice, it can fill in the map. There you go. So I think we can end a little bit early, but first just hang on for 2 minutes if anyone has any questions about particle filtering. Yeah.
I'm a little confused about the weighting process. So you downscale first and then scale it back up.
Right. So you downweight according to the probability they assign to the evidence. So this blue one apparently only assigned a 20% chance to what you actually saw. This green one assigned a 90% chance to what you actually saw. And so you downweight this by 0.2, you downweight this by 0.9, and now you scale them all back up accordingly. So you're basically sampling from this new distribution, but it has to be normalized.
So the probabilities on the left, is that from what
These are not Are you looking at this column? These are the different states. This is like the coordinates that we're talking about. So the green one is in 3,2. So initially they're all basically having probability 1 over n, where n is the number of particles. And now this is really 0.9 over n and 0.2 over n. And these aren't going to sum up to 1 when we sum over all n of them. So we have to scale them all up by some constant factor. And that's our new distribution. And that looks like this, I guess. So now these numbers all sum to 1. I guess it's The way it's drawn, it's not really scaling them up because we're doing the divide by n thing there. But yeah. Any other questions about how this works? Yeah. Down weighting, well, if they all start, okay, so I would have written these out as like 0.9 over n, or like they start with 1 over n each, and now at this it's 0.9 over n, 0.2 over n, 0.9 over n. Because all these, nothing's ever going to assign more than probability 1 to the evidence, and so it's down weighting because all these numbers are going to be less than 1. It's just some are down weighted more than others. Yeah. Uh-huh. So you're never going to, at this resampling thing, you're never going to get new particles. That was why I was talking about how like you're never going to get new maps if you just did pure particle filtering, because you're never getting new particles at this step. You're just getting more copies of some of the particles you already have. When you transition, you'll get new, the particles will move because the transition matrix moves. But again, in the mapping example, the map never changes in the transition matrix. And so that's why you'd never get a new map. But yeah, so you're keeping the same particles as before, but the number of them will change. Yeah. Yeah. All right, if you guys can, if anyone else has any questions, just come up.